welcome to the new class on of the knowledge representation on the web course. My name is Ilaria Figli, and today we will be looking at how to characterize knowledge graphs with a particular focus on knowledge graph measures. So just to recap a bit where we are and what we did, we've been looking at creating and saving knowledge graphs, adding meaning through RDF and OWL semantics. We looked into ontology engineering in order to build large-scale knowledge graphs on the web. And we looked at Sparko as a language to query knowledge graphs, and Shako as an additional way to verify knowledge graph constraints. We are now moving into more practical topics, and today we will be looking at how to characterize a knowledge graph that you're working on and how to perform clustering over this. Just to start with a bit of motivation, why do you need to characterize the knowledge graphs? Most of the time, these measures and these techniques allow you to characterize, to describe the knowledge graph that you have created. It allows to show differences to other knowledge graphs that exist. And mostly summarizing multiple knowledge graphs and their properties, for example, when you use them in a given experiment. Usually this information comes in the form of a table, whether this is a characterization, a summary, statistics, involving the number of relationships, the number of entities. So you try to give information to the readers about the knowledge graph that you are working on. One of the very first things you might want to do is to compute the size of a knowledge graph. There's different ways to look at this. The basic way is to compute the size in terms of number of entities, number of properties or relationships that the graph contains, number of triples overall. This is usually seen in papers that might use a knowledge graph as a data set for testing a new method. There are more advanced ways to compute the size of a knowledge graph, and this is especially used by methods that are looking into understanding the semantics behind the graph that they are operating with, and how this impacts their method. So these measures can be the number of classes, the number of annotations, the number of subclasses or subclass triples that you might have. And finally, you have semantic measures that describe the size of the knowledge graph. And these are typically used when you want to give a full characterization of a knowledge graph in terms of a data set. And then these measures focus on the description of what is contained in a knowledge graph. Usually this involves the number and type of restrictions that the knowledge graph includes, that the schema of the knowledge graph includes, the coverage of the domain, the consistency, the type of description, logic that is being used, whether there are violations, and so on and so forth. Practically speaking, how do we compute size of a knowledge graph? There is no direct library in Python. We are using Python in our course. There is no library that provides you with these methods directly. A lazy method is to upload your knowledge graph into protégé. And then protégé is the ontology engineering editing tool. And as soon as you load your knowledge graph, you have these ontology metrics for free. So you can get the number of axioms, number of classes, number of object properties, information about the individuals, information about annotations, and so on. An alternative way is to query your knowledge graph using Sparkle, which means you formulate Sparkle queries that then can allow you to retrieve the information you want. This works both at class level and instance level, so you get information from the entire graph. In terms of a knowledge graph measures, so these are measures that are specific to a knowledge graph and not any graph. There is a number of measures that you might be interested in assessing. We divide them between basic and advanced. You can compute number of entities. We are talking about classes and individuals combined. So this is the schema level and the data level together. The number of properties, so what are the how many properties are being used, how rich is your knowledge graph, the number of triples and axioms overall. Then you can, so these are the basic ones, where you combine schema and data together. You can then move into more advanced knowledge graph measures. This includes the number of classes, so this is at schema level, or at instance level, the number of individuals for a given class. You could also include information about annotations. Annotations are usually these properties that provide you information about the entities you are describing. So whenever you state an RDFS label, RDFS comment, RDFS description, these are all annotations over your data. And a typical measure is the coverage of annotations, which is a ratio between the entities that you represent and the annotations that they include. In order to measure a knowledge graph, the first step that you need to do is to convert it into a mathematical graph. So if you recall from the previous lectures, we have defined a knowledge graph as a named mathematical graph, which means that in a knowledge graph, you have labels over your nodes, names over your nodes, and names over your edges. You can decide to convert your graph into mathematical graph, but remember that this ignores the semantics that your graph includes. So all the restrictions, the difference between classes and instances is completely lost. So the class and instance level is totally mixed. This doesn't mean that you cannot use it, but you need to take this into account while working on a converted graph. There's different type of graphs and different type of algorithms that you can use once you have converted your knowledge graph. Most of this conversion can be performed in Python through a library called NetworkX, which you are required to install for this course. We talk about graphs as an undirected graph and a D-graph as a directed graph. You might have multi-graph where you have multiple connections between the nodes in an undirected graph. And we talk about multi-digraph when your connections are directed. A DAG is often defined as a directed acyclic graphs. So there's no cycles in the path between the nodes. Remember that not all the algorithms work on with all types of graphs. So you need to be aware of the type of graph you are choosing the conversion in order to choose the algorithm. So make sure your choice is well thought. Once you have converted your graph, you can then calculate the typical graph measures. The graph community is, and as well as the social network community, is a much older and bigger community than the semantic web one. And they have been looking at ways to characterize a mathematical graph for a long time. This means that the knowledge graph community can also make use of it once you convert your graphs into data formats that can be used. As we said, Network X, the Python library, provides a very good explanation of the different measures and a number of algorithms to perform manipulation over these graphs. If you are looking for a visual tool, you might also want to check out Gephi, which is a tool for graph visualization and manipulation, which also includes an RDF plugin in case you might be interested. We are going to briefly look at the graph measures that we include in this course. As we said, the best way is to test these measures and look at these measures in Network X. We talk about size of the graph. We talked about it already a few slides ago, including the number of edges and number of nodes, which means number of classes and number of properties in our case. We talk about density. This is mostly computing how strong the connection in your graph might be. We talk about a number of measures that allow you to measure global and local centrality. This is in degree and out degree of a node, so how this is connected with respect to its neighbors, closeness and betweenness, really look at the connectivity of the neighbors around the node, as well as eigenvector centrality. And PageRank mostly looked into the probability of a random walker to randomly choose an outgoing link when traveling from a node to another one. Another interesting measure is a clustering coefficient, so how your nodes behave when performing clustering over your graphs. In terms of what do we mean by clustering is that we take our graph or our knowledge graphs and we try to identify community. In this picture, they are marked through colors, and we try to understand what these communities are about. There are no established methods for performing clustering over knowledge graphs. They often depend on the task that you have at hand, and they are not really well integrated with the libraries that we use, especially the libraries that we use that allow to perform operation over knowledge graphs. What you can do is that you can convert your graph into a mathematical graph again, and then perform your clustering. So what you do is that you perform your conversion. You run your reasoning engine in order to compute all the missing links. So the asserted and inferred graphs are both included in G. You might need to remove certain information wherever appropriate, and then you can apply clustering algorithms that you find in Network X and CD-lib. This is also a library for performing clustering over graphs. And what you end up with is a set of clusters in your graph that you can then further analyze to try to maybe give them names, understand what their topics. You can analyze them in a number of ways. In terms of clustering algorithms that we look at in this course, we mostly talk about the Louvain clustering algorithm. It's often a safe choice if you are clustering you're trying to identify communities. Communities or cluster is the same thing in our setting. You can choose Louvain. It has been proven that sometimes it might be a bit biased, and it might create communities or clusters that are not strongly connected. One solution is to choose the Leiden clustering algorithm as an extension of Louvain. Both algorithms perform a heuristic search to try to optimize what is called cluster modularity. So this is a density of the edge inside the community with respect to the density of the edges outside the community. The ultimate goal is to identify which are the edges that create a higher density within a cluster with respect to outside the cluster. Network X only includes Louvain, and that's why we are also looking at CD-lib, as it provides many more implementations, including the Leiden clustering. This is the end of the knowledge base on knowledge graph measures. Thank you very much.